Okay, welcome back to the next part of slides on Multimediale Werkzeuge. So we just saw the meaning of the DCT subbands and now about how we can use them for compression and for using the principles of compression, which is irrelevance and redundancy reduction. So here's also a reference to the literature. So this is one of our book chapters. There's this book on book of the media informatics, and the authors, the editors are Kai Bruns and Klaus Meyer-Wegner, and there's a chapter bars on compression. So this should be editors. This should be media informatics. Yeah, so here are some definitions. First, what is irrelevance? Irrelevance is the part of the information that cannot be perceived by the recipient, for instance, the eye. So here, for instance, the eye. Yeah, example here, details in an image that the eye cannot perceive is indicated, for instance, by the contrast sensitivity function. Remember, we saw which spatial frequencies the eye is more sensitive or less sensitive to. So we can use that for compression. We can represent details or spatial frequencies for which the eye is more sensitive with more bits than details or spatial frequencies for which the eye is less sensitive. But for this, of course, we need to be able to distinguish different spatial frequencies, and this is what the DCT does for us, right? The DCT decomposes the image into different spatial frequencies. Then we have redundancy. This is the data that does not provide additional information about the source. For instance, the statistical dependencies in the data of a source. In the image, for example, uniform surfaces that often occur when neighboring pixels are very similar to each other. So in that case, we can use, for instance, run length coding by just saying how often we want to repeat a certain value, and that is a very compact representation, even though it may cover many pixels. Yeah, and in images we often have this case that neighboring pixels are very similar. Right. So maybe I should say in images, because it's quite often. Uniform surfaces often occur. Yeah. So compression with a DCT benefits from the fact that pronounced edges or fast transitions in images are rare, otherwise they would cause bits, right? Because they contain high frequencies. So here we benefit from the fact that we mostly have more or less even surfaces. Yeah, and by sorting the DCT coefficients into images of the subbands, we got a space frequency representation, as I mentioned, which means each image of the subbands is a representation in the spatial domain, but with reduced spatial resolution. Right. So, because these images also belong to a certain subband, they also represent a certain frequency range. So we have both space and frequency. And we can already apply lossless compression in the DCT domain because of this energy compaction, right? So if we have energy compaction, then the DC values appear much more often, and the DC coefficients, I should say, have high values, and then low values at high frequencies appear much more often. So then we can apply entropy coding, for instance Huffman coding, and in this way we can reduce the bit rate. And this is important, for instance, for medical application, because here we don't remove any information. We just have a more compact representation, right? We can still access or evaluate all the information that is still present in the image. Right, so lossless compression is important, but it only gives us a limited compression performance. But with DCT, with the DCT transform, we can obtain lossless compression. If you want to have more compression, we need lossy coding that uses the different sensitivities of the eye to different spatial frequencies, as can be seen in the contrast sensitivity function. Right. So the eye is less sensitive to higher spatial frequencies, and the coefficients of the higher spatial frequencies can be more coarsely quantized without the eye noticing it. So this is how we would use the irrelevance reduction. So here you can see the contrast sensitivity function again. Just the principle. Here horizontally you have the spatial frequencies in periods per degree. Vertically we have the contrast sensitivity of the eye, and here you can see for which frequencies the eye is most sensitive and which frequencies are less obvious to the eye. So we can see there's a difference between brightness and color. So here the luminance, the chrominance, and you can see they have different peaks, and this is because of the different number of the light sensitive cones and rods in the eye. Yeah, and the frequency axis now needs to be connected to the DCT subbands, right? And that also depends on the resolution of our image, which means how many pixels do we have in our image, and also on the viewing distance. Right? Remember, here we have periods per degree, and that means this degree depends on the viewing distance and the resolution of our screen. And that means we need to have an assumption of the viewing circumstances, meaning the resolution of the screen and the viewing distance. And then we can do a mapping between the DCT subbands to this spatial frequency axis, the periods per degree. Yeah, so here I have an example. So here we have black and red, and each represent a different case for the viewing distance. So it's not precise, it's just showing the difference. So when you have a distance which is further apart, then you would have those bands squeezed tighter together. No, the other way around. Then it becoming further apart, because everything appears as higher frequencies, meaning when you go further away, then everything appears finer and finer, so everything is shifted to higher frequencies, every pattern. Yeah, so this shows we need to make an assumption for the viewing circumstances. Yeah, so this is what I just mentioned. We assume a certain viewing distance for a certain pixel size, and in this way we can then do the mapping from the DCT subbands to the contrast sensitivity function to obtain the best quantization step sizes. Okay, and that's it for this set of slides. Yeah, thanks for your attention, and then see you for the next slide set.